Hello, everybody. My name is Min. I am a assistant professor at Department of Computer Science and Engineering at the University of Notre Dame. So after we have learned a lot about domain-independent text mining technologies that can absolutely be applied to sciences, here I want to introduce two works that are specifically designed for scientific knowledge extraction. They try to address unique challenges in sciences. So one is when we are looking for scientific statements, the conditions of the observation or hypothesis are essential, right? Think that we may have different kinds of conclusions or observations when the environment are different. For example, at different time, different temperature, different pH value, or using different equipment, the observation could be different, right? Say whether a chemical can kill a kind of bacteria, right? So condition is very essential. And the other thing is, besides the text data, tabular data are very common, ubiquitous in the scientific literature. So whether we can extract the evidence, especially for experimental evidence, because we usually use tables and figures as well. Well, figures is more difficult, right, for extraction. So we use tables to describe to present the experimental results and do analysis in our research publications. So how can we extract the experimental evidence from the tabular data in sciences is a very interesting task. So one work was published for the conditional statement extraction is in KDD 19, and the very recent one that is experimental evidence extraction in data science is published in TripleDub. So for the first one, so the goal here is to turn text data into knowledge graph. If we can use machine learning technologies to turn the unstructured scientific literature into scientific knowledge graph, we can do knowledge inference, we can do reasoning, we can do search, very, very efficient search, and we can generate novel hypotheses from the knowledge graph. So there's so many applications that could be enabled when we have the structured knowledge from the literature. Well, when we construct knowledge graph, think that in a generic domain, the general domain. So if we have news talking about LeBron James is returning to Miami Heat, so Miami Heat is is an NBA team, okay? So we want to extract the nodes, the entity nodes in such as LeBron James and Miami Heat, and also the relation between the two things, say it is returning to, right? So so why do we want to structure this text into a knowledge graph? Because it will be easier for us to understand the information, and also can help us to identify what's a fake news. This is actually a rumor, right? So after several years in Cleveland, LeBron James, people think about whether LeBron James will return to Miami Heat or not. And actually his decision is to join Los Angeles Lakers. He's now a Lakers player. So when we have a lot of information that have been structured into the knowledge graph, then we can say, see here, quite a lot of outgoing links from the LeBron James that is returning to or joining the team. Well, most of them are connected to Los Angeles Lakers, not Miami Heat. Miami Heat is a minority. So we may be able to infer from this kind of difference of frequency to know that, Miami Heat, returning to Miami Heat is actually a rumor. It's false. So that's how we can use the knowledge graph that have structured knowledge for a lot of kinds of applications. So for sciences, we also want to construct knowledge graph. The problem is, let's see here. So when we try to extract the fact tuples, which were like just a triplet here, right? LeBron James returning to Heat. We may not only have fact tuples, we also need condition tuples. Let's see, for this kind of sentence, right? Let's take some seconds to read the sentence. You'll see acidic pH reduces activity and alkaline pH increases activity. So, one sentence may have multiple fact tuples, and one or multiple condition tuples. Serial condition is like the channels. The channels are in the T cells, not in any other kind of cells, right? So this is condition. And also, it's no longer a triplet, right? The relation may be between the concepts, but it could also be between concept and attribute, or that between the attributes. So here you can see what is reduced. It's the activity of the channels. It's not the channels themselves. It's the activity of the channels. So extracting the attribute of the concept and use the attribute as a subject or object is very important. We cannot just rely on a triplet. Another kind of condition is, like see here, the activation of thymophocyte or production of cytokines. So you can see here during these two kinds of periods, which are very essential for the main clause about the main observation. So we should extract such kind of multiple condition tuples from the sentence, right? So once we got the fact tuples, we know that it could be multiple fact tuples, multiple condition tuples. How can we represent the information as a knowledge graph, right? It should not be a flat knowledge graph that we used in general domain. It should be a multiple layers. Let's see here. The first layer we design is the entities and their attributes. We attach the attribute like activity to the entities, right, to the concepts. And the second layer, we have the relation, which can connect to the subject node and object node. So subject could be, subject and object, they can be concept, they can be attributes. And a statement, which is the information source of this structure, the statement sentence is on the top layer. It connects to the multiple tuples. It's actually connecting to the relation nodes on the second layer, right, of the multiple tuples. So once we got this kind of three-level scientific knowledge graph, then we can do inference. But note down here is this knowledge graph is no longer flat. It's not homogeneous, it's heterogeneous, and it's multi-layer. So making the knowledge graph more complicated. Fortunately, we have a lot of kind of complex graph mining algorithms, in network science, in data mining, a lot of kinds of communities we are trying to understand and investigate those kind of data. So those algorithms can absolutely be utilized to analyze this kind of data that we structured from the literature. This is another example. And this is another example. Say, how can we represent the condition tuples into a knowledge graph in 3 layers? Okay, then the question is, how can we build this knowledge graph? How can we extract the fact tuples and the condition tuples? Okay, so the idea here is probably can translate this kind of task as a sequence labeling problem. Given a sentence for one tuple, suppose we are looking for this first fact tuple here, acidic pH reduces the activity of the channels. We want to tag the tokens of the sentence. If that's not in the sentence, it's giving the O down here. But if it's, so see here, this label is BF1C, means this token is a beginning word. B is for beginning word of a concept. C is for concept. It's not an attribute, it's a concept. In the subject of this tuple, right? In the subject of this tuple. And the tuple is a fact tuple. Okay, it's a fact tuple. It's not a condition tuple, it's a fact tuple. So begin, fact, subject, concept. All these dimensions form this unique label that we want to predict on this word. Okay, so we can then label on all the tokens. Like this one is the beginning word of the fact relation predicate word, and this is the fact object attribute. Okay, so we can have all these labels to tag on the sequence. And you know that we are looking for not just one fact tuple, we're looking for one or multiple fact tuples and one or multiple condition tuples. So that is how we should generate multiple sequences. So it's no longer a single output. We are looking for multi-output, right? Each output sequence should be mapped to, generate a tuple that we are looking for. See here, we have 3 sequences we're looking for, and they can be transformed into these tuples. Suppose we were able to annotate the data to say in the training data, these are the tuples we are looking for, and we can easily generate the output sequences for training. Now here I like to show how we annotate data. So we build a toolkit, an online toolkit, so that annotators can, we recruit 3 annotators to do the work, and they can just put the words or the phrases into the blanks, and they can add new facts, new conditions. Eventually, they got all the things, and we transform that into the tuples into the sequence labels. So we have, how many labels we have? We have 21 labels, right? 21 labels, because we have beginning word, B or I, we have the fact or condition, F or C, 1, 2, 3 for subject, relation, or object, and C, A, P for concept, attribute, and predicate. So that's how we can have, we have 21 labels. So this kind of prediction task is it's a multi-class classification. It's not easy at all, right? It has so many classes. It's very challenging. So, and it takes so much time to have the experts to annotate the data. So we collected 31 random paper abstracts from the PubMed, and each annotator needs 30 minutes, more than 30 minutes to annotate one single document that have just like around 10 sentences. So eventually we got 336 annotated sentences, and you know, you can see the number like 750 fact tuples and the 650 condition tuples. So that's not easy to have all these annotations. Very expensive. The good thing is this number of can still be used for training anyway. While you can see that the number of condition tuples is comparable with the number of fact tuples, which means that condition does matter, right? Condition is very important. It's an essential rule in the statements. Our scientists, when they write the statements, they try to be really precise, accurate. So we always write down the condition if there's any condition. Okay, as we have very limited annotation for training, then another idea, you know, one straightforward idea is whether we can leverage the large amount of unlabeled data to improve the performance. Well, when we have only like 336 annotated sentences, actually we have 140 million unlabeled sentences. Whether we can we use those kind of information to improve performance? So before that, we are thinking about, okay, actually, yeah, we need more information to generate the output sequences. We can extract more informative features, such as, you know, the part of speech tags, right? These POS tags can be really useful, and the phrases or the concept detection and attribute discovery. All those kind of technologies have been studied and proposed. Even in our group, we have posted that many technologies for these tasks. So those signals can be transformed into multiple input sequences to give more features for the sequential models to learn, to label the data. So you can see, instead of using only one single sequence of the words, we can have this sequence. What is this one? This is a input sequence of the part of speech tags, right? And this is when we use phrase mining technologies to identify the phrases for P here and identify the attributes and the concepts, then we can use that information to form the input sequences. So actually for part of speech, it's very, you know, you can see that it's really useful, right? Say, when they are all about like the fact concepts, so they're usually phrases and they're nouns, noun phrases. And when it comes to the predicate in the relation, it's a verb. And those kind of part of speech can give a lot of information to help to alleviate the difficulty of predicting the token labels than just using the words themselves. Okay, we evaluate the performance on the data we have. So you can see here this MIMO framework, which is in short for multi-input, multi-output. It can improve the performance, right? I'm just let's take a few seconds to look at this table, and you will see it is predicting the labels of the tokens, how accurate it could be, and this is how accurate we can extract the tuples. So yeah, the quite interesting here here is for the encoder. When we replace the encoder from replace the bidirectional LSTM by BERT, is significantly improved performance. Well, you can see that MIMO on this BIOSTM can improve by like around 7 or 3 or 7 or 6 or 7 points. While when we replace with BERT, is even outperform the MIMO for BIOSTM. So then we further try MIMO on BERT. You can see the performance comes to 81, around 81 point. Okay, so it's pretty good to show that this MIMO can consistently improve any kind of framework trying to do sequence labeling. Yeah. Then a case study down here is, see, we can use this MIMO technology to extract a knowledge graph, right? Then we can see what can increase the cell proliferation and what reduce the cell proliferation. Two different kinds of relations connecting to different subjects, okay, that will have different impact on cell proliferation. And each impact or the four statements were observed in different kinds of conditions, right? So this is pretty informative to help the scientists to understand. So what will have, what kind of treatment, what kind of medicine will have impact on the cell proliferation. Yeah. This is another example. Okay, increase and decrease, increase and reduce for different condition in different types of cells, right? Different types of cells. Okay. Then let's come to the second work. The second work is to extract the experimental evidence from data science. Why? Why do we do that? So here is our motivation. Actually, when we initiated this project with my students, asked him to study a task called multi-label classification. And it's actually called extreme classification, which means when the number of labels is extremely big. It could be the millions of labels. Some applications could be, say, we try to predict the labels of the products on Amazon product page. Right? We may have millions of labels, such as cheap, red color, comfortable, useful, and you have millions of labels, and you may have each product may have 5 or 10 labels. We try to predict or recommend labels for the users, for the reviewers. So this task is called extreme classification because you have so many labels, and it's a multi-label classification task. When my student was reading those papers, and he found 2 papers that are quite interesting in 2017 KDD conference. One is this one by CMU, UT Austin, and Penton. So you can see here, they show the performance down here. This is there are quite a few data sets that are standard, right? They tried Amazon data, Wiki data, Delicious data, right? Amazon category data. And the multiple baseline methods, they propose this PPD sparse. They show that this PPD sparse is faster and more accurate than the baseline methods. Let's focus, let's focus on this one. Let's suppose we are looking for this this measurement, precision at 3 for Delicious. Okay, Delicious precision at 3. Fast XML, which is a baseline method, I think it's 2014, and the value is 4284. Okay, 4284. Actually, there's another paper in the same year, also in KDD. It's by Yahoo Japan, working on the same problem, but a different methodology. Well, they also compare with the baselines, okay, including the fast XML. And they also use very standard data sets, Amazon, Wiki, Delicious. Then they use very standard metrics, precision 1 and 3 and 5. So let's look at that one. Do remember, we are looking at this precision at 3 for fast XML, Delicious. Okay, for the 2. FoxML, Delicious, precision at 3, 38. They are different, but it's not too surprisingly different, right? It could be caused by some random generation or some hyperparameters, for different implementation. That makes sense. However, sometimes a small improvement can already be like claim a significant contribution in the science, right? So let's see, if we put all the numbers all together in this table, the left hand are the numbers reported by the first KDD work, and the right hand is the numbers reported by the Yahoo Japan's work. Then you can compare, right? Quite a few are different, and the underlined pairs are for those that the difference bigger than 3%. See, some difference that could be really significant, like here for delicious, the P-FAST3 XML, right? The CMU work, in their implementation, they can only achieve 26 or 23, while in the implementation by the Yahoo Japan, they got 37, 35, right? Here, for the PD spare, it's 87, but the other is 74. Significant difference, right? Say, that comes to be our motivation. If we want to know what is the state-of-the-art performance, can we build an experimental evidence database from all the scientific literature, I mean, in data science altogether, so that we can know, okay, check which this kind of conflicting numbers, and then we can know what could be the best performance of the existing technologies. So that comes to this work. It's in TripleW. The paper title is Experimental Evidence Extraction System in Data Science with Hybrid Table Features and Ensemble Learning. So we choose data science because it's a field that we know very well. So there are multiple kinds of tasks, like a multi-label classification, recommendation systems. We look at different kinds of applications and collect a lot of papers on that. And I've showed an example in the extreme classification, right? So a research study will do the literature survey and eventually generate the experimental evidence. So then when people try to give evidence down here, we usually give a score on a specific data set using a specific method. It could be a baseline method, it could be a proposed method, and a metric, right? So these four things are most important in the evidence: data set, method, metric, and score. And also definitely want to trace back to the source of this evidence, which is that paper, right? And if we can have a lot of fact tuples extracted from the literature, then we can try to answer these questions. We can use this information to answer the question like, what are the data sets we can use for a certain task? And how do people evaluate the methods, right? What kind of metrics? And what's the state of the art? So eventually we can get this kind of extraction system. So how can we do that? So we propose to use feature extraction and different kinds of learning strategies. Let me introduce the details there. So for the system pipeline, the first step is to collect the PDF files, the papers from digital libraries, and cropping the tables from the PDF. And based on that table, we try to align all them together into one single experimental result database. We call it ERD. This is actually the most challenging task. How can we identify the column headers, the row headers, to identify each cell of the cell values in the tables, to know how to align the cells into our integrated database. And once the database is built, we can use a SQL or PHP to set up some search applications, right? Search functions. So, okay, go from table to that database, to the ERD. So we first have to parse the table. What are the components of the table? The table may have a textual caption, right? We call it D. And the table may have row names, have column names, and column indicator, name indicator, right? So here, the W here, it indicates that these column names are oh no, the name indicators indicate these row names, right? The row names are algorithms, right? And the table body. So the table body means they got this table body, and each cell is mapped to a certain row, a certain column, and the caption, right? So that's a component of a table. So this is the most, it's probably the simplest table so which has the column names, the row names. It's just a single column header, single row a single line of column headers and a single line of row headers and the body. But we may have multiple kinds of templates. People are really good at design experimental result tables for in their papers, right? Very fancy tables. So like we maybe have double lines of column headers. We may have double lines of row headers, and even double for both. So we identify these 8 kinds of templates of the tables, and totally actually they cover more than 95% of the tables in our data. So if you look at the amount, also the percentage of the templates, we find that the template D and the E are the most popular. So the D here, which have double lines of column headers, and also this one. So this one has the row name indicator, which this one doesn't have the row name indicator. Okay, they are the most popular table design, which means we really like 2 lines of column headers, right? Okay, so the problem definition is from the words or the tokens in the table caption, and also the names of the columns or names of the rows. We want to match them to identify the type, right? The type of this the names. It could be data set, or it could be method or metric, so that we will map the cell values to the database. Yeah, so the first task is to classify the concepts into the categories, and then unify. Second is to unify the cells into the tuples, method, data sets, metric, score. Okay. We propose to do ensemble learning. That is, we will leverage 2 kinds of methodologies. One is rules. We propose 3 rules. We'll talk about the 3 rules later. That's based on 3 assumptions, and also use the embeddings, repetitions to in the learning classification models. And then we run it iteratively using some seeds to run it iteratively to find the performance, and to improve performance. So the first assumption is the row or column header indication, right? So if the row names, I'll say the indicator words are like algorithm or method, then it's talking about, say, the row headers are likely to be method, right? To be method. So a dictionary of this, so by learning a mapping function from the indicator word to the type is very useful. The second is the type consistency. It says that the column names in the same table or the row names in the same table should have the same type. It's a consistent in the table. So that's also a kind of rule that we can apply. And the third one is one table should cover all the 3 types: method, metric, and data set, all the 3. So if we find that something is missing in the table, for example, here the data set is missing in the table, we should go to the caption to look for a word representing the data set, which is this Twitter data set. And the 3 kinds of embedding features that we use in the learning classifiers are the concept embedding. We run BERT to get this concept embedding. And the other is HEBE. We run this heterogeneous network embedding learning to find the representations and build a classifier with these features. So given the scene concepts, we harvested from the rule-based classifiers and the seed, and then we can predict the types of these unseen concepts, and we choose the most confident one for the next run seed to do it iteratively. Okay, let's review this Tablepedia system that we go from data science papers to a large experimental evidence extraction system. So the first is table extraction, right? We try to crop in the tables from PDF and recognizing templates and clean the table, and then do unification, including classify the row and column names, also words in the captions into the types, into category. We have 3 categories: method, metric, and data set. And then unify the cell values in the tables into a large database. It's construction. And eventually we use database operations to do QA on this database. So some results down here, it shows that, it takes seconds to read the table, but then you will see all the rules and all the two kinds of embeddings are very useful. Actually, rules perform better than learning. It's quite interesting, right? Rules performs better than learning because those rules are pretty robust. Right? They are very, very informative rules, like covering all the three types and also consistency of the type of the column headers and row headers. So some results down here for each type. You can see that the red curve is the combination of all the rules and features. It performs best. And semantic embedding is much better than network embedding. This is also interesting. Okay, for recombinant system, we show that table for multi-label classification, right? Here, I want to show a table for results on recombinant systems. So here are like 3 example papers on ACM toys, TEAST, and wisdom. All the tables about recombinant systems in performance on opinion data sets. So we can integrate all the cells into this kind of database. Then you will see, okay, actually there are conflicts, right? For the user mean is like a user-based equilibrium filtering method, I think. Then the on the opinion data set, which is the same data set using the same metric, MAE, mean average error, mean absolute error, sorry. So the scores are different, right? For different tables, different papers. And also the red blocks showing the conflicts in the results. And the greens are showing the consistency, right? So in different papers, different tables, and for the same tuple, the same method, data set, and metric, the values are the same, consistent. So this is pretty impressive, right? And the last line say, when here is it's error metric, the smallest should be the best performance, right? So we can see, okay, on our MSC metric, the best performance on opinions is this one, the line 127. So then we can enable quite a few QA tasks on this database. We're trying to find, the first is to find the related methods and metrics and data sets. How many methods can be used for opinion? In our small data that we crowd from very recent 4 conferences for 4 years, not more than 4 years, but 4 conferences, over 10 years, I think. KDD, ICDM, triple-up, and wisdom. So 36 methods. And if we can expand the set of the papers we collected, we can have more, right? Can have more. And what kind of metrics can be used for Amazon data? Precision recall F1, more than 15. And how many datasets were used with Amazon in the same table? Which means that who compare their methods on multiple datasets. So DBLP with Amazon, Wikipedia with Amazon, more than 50. So what's a top performing method on a data set? If you give the metric, you give the data set, it can return you top 3. The top 3 for F1, right? Top 3 methods. And also you can find the source of the papers. And also the last one is to find the conflicting numbers. We can recover what we presented in this table from our database when you do this query. Okay, that's all for this part of talk. Thank you very much.